Mine's happy.
When do they begin playing that?
Friday. It's very annoying because there's many days of no baseball. Nobody's what to do in myself. So it is what it is.
You gonna go to one of them?
Be in LA?
Unless I saw some feedbacks.
Where are they listing it?
Yeah, first 2 in LA, then 3 in New York, and then 2 in LA. But it's about 7.
Yeah.
Still have to win 4. It could be over in 4 games. Or it will be, but.
Okay. How's the homework going?
I think I'm not better.
We're fairly behind schedule. That's okay. You know, learning is one of the goals of the class. So it's not just me standing up here performing for an hour. I think I'm probably still gonna assign the homework that is coming up. So it'll just have more like Orbity shit. You'll be like, oh, now I get it better. But I may change the deadline, so or everything will just start to slip. I don't know if that's easier. Yeah, obviously.
Do you know when you're gonna release the next assignment?
Well, I was gonna wait to get this. Once I get, you know, I'm free. It's like, it'll just gonna stop working. And see how much your revisions. For a couple of the problems, I had some really good feedback. Folks were curious about,
Howdy. Folks are curious about, say, problem 3.
I noticed there is consistent misunderstanding. So let's remember a couple different things. I'm going to draw the coordinate system. And this is the moon, right? This is the Earth. And I want to know about the tides here. Okay? We're just setting up the problem, and as soon as I set up the problem, you'll recognize the issue. So the first question is, this is X, by the way. This is Y. First question is, where is big M?
That's the moon, right?
That's the moon, correct? So that's over here. How far away is the moon? A distance R. Good. So that's this total distance. R. And note that's from the origin, where we centered the origin around there. And M is the location, or I should say, let's say X here, is the location of little. So what are the competition of forces at this location? Which direction? Which direction? Which force?
Oh.
Well, the net force, I prove, or I make you prove it is to the right, but that's not what I'm asking. What are the forces that go into the net force?
Gravitational.
Gravitational what?
Gravitational force from the Earth.
Is that what you consider for the tides? Right. So in class, we had the bigger body, and we were thinking about raising tides on the small body, right? And so we had basically the opposite looking algebra. But here, it's really important to remember that this gravitational acceleration is towards the moon, right? So I have F, G is towards the moon. Is that the only force to consider? No, why not?
Because the total force with 0, so there has to be a constant force.
Do total forces have to be equal to 0? Yeah. That's true in one circumstance, like I'll show you a different circumstance, but that's not what I mean here. At the center, that will certainly be the case because the Earth is not okay. The whole point here is to create an acceleration that the tides. I have the force of gravity. Are there any other forces? Is that a force? That's what we're going to calculate. Tidal forces are a combination of forces. And I'm asking what forces do I have to consider in this picture? Okay, what is that?
Is what the mirror part. Is it orbiting?
That's a very good question. So you're thinking about, is the moon orbiting the Earth? Is that true? Yes. So is this picture correct? No, what else am I including here? If I want to keep the moon here, or the Earth here, and the moon here, what do I have to do to make this picture true? Rotate the frame. So I have some frame rotation, like this, at some speed omega, right? Does that introduce any forces? Centripetal force. Which direction does that go? Okay. So here's a really important question. Okay, if I'm thinking about the tides that are being raised on the Earth, and I rotate the frame to keep this guy where he is, which direction does the centripetal rotation want to throw me out? You say outwards. Really careful about the word outwards here. I don't disagree that it's going to be perpendicular, right? Question is this way or that way? Why that way?
I think that's forces each other, so if they're pulling on each other.
Okay, let's think of it this way. We have a big disc, it's rotating. Okay, it's going around like this, spinning. I take a ball, it's going to fly outwards from the center of that disc, right? That's what we think about it. But for Earth Moon system, they already saw the example of the moon going around. And we asked the question, which direction would the moon keep going if you turned off gravity? Fly. Okay. What if the moon is the one being held and the frame is rotating? Yeah, so if you move into the frame of the moon, then it looks like the Earth goes around. And what's the direction of that? It's out, but in the moon's frame, it's the opposite direction. The centripetal acceleration for the Earth looks like it goes out that way. The centripetal acceleration for the moon looks like it goes out that way. So this is a smaller force this way, right? Due to the fact that it's rotating. And then we can do something like something like force effective is going to be equal to Fg plus Fc, and remember that these are vector quantities, so on and so forth, right? Now it's also really important to write these distances properly. What is FG? Very good. What's this one? I'm gonna use the negative because it's going the opposite direction. We said that if we set the center, right, this part of the earth should not move, then these should be in balance. And so we get a definition for omega squared, which is G M over R squared. Or sorry, R cubed. Right? Reasonable? Okay, this is what we did in class. There's nothing new here. We plug this back in, and all I need to do is I need to be careful. So I'm gonna rewrite this now. And I'm not gonna write R squared here. Nor am I gonna write, here's G M. Okay. I'm gonna put R cubed on the bottom. I need to be very careful about what I put in for R. This would be R minus X, right? Because it's not the full distance to the center, it's this. Okay, so this is R minus X, and this is R minus X. And that's my force, right? Tidal force. So if I want to approximate my tidal force, I use this. Literally. And this gives me an example of what the tidal force is going to feel like, that location. Because this, of course, is not generally true. Right? This is the differential. How is gravity changing over a small section? And that would be a description of tidal force. Remember, the tidal forces, they can be combinations of forces. Difference of gravity. Okay, good. What else do I need to tell you? What else do I need to tell you? For problem 4, and you're doing medium motion resonances. So we're looking again at orbits that have integer multiples of their periods. So hopefully you got the right choices. I think there was 5. You only have to pick 3 because there's 5 to choose. So just make sure you didn't pick the wrong one. And then the major question is how do we go about thinking, let's say I can't fly there and I don't have any pictures of these moons yet. Can you predict what the surface will look like based on any availability of tidal heating? How would you possibly estimate? Well, let's say you do know what Io looks like, or you do know what Europa looks like. You can estimate the change in gravitational force. How would you do that? Assume it's a Jupiter. Assume I have some body. A moon. It gets closer and farther away. What does it feel the largest tidal gravitational? Yeah, exactly right. And sorry, let's call it periapse. Periapse is the closer one, right? A is far away. Periapse. Okay. And over here, apoapse. Okay. So this is when it's close. How far is this, by the way? Can I write that in terms of things that I know? Yeah, what's the minimum in terms of the things that I know about the ellipse? Yeah, what does the R mean there? Yeah, so this R, we have to be a little careful here, right? So really the things that I know about the ellipse are like the semi-major axis, A. Is be 1 minus E. Right? And then this one here would be what?
The 1 plus.
A 1 plus E. Right? Okay. So I could write R equals that here, and I could write R equals that here. And let's say I want to understand the delta G or the delta F, you know, I really just want to know what is the change in the gravitational acceleration at those two different points. Because if it's big, say bigger than Io's, then I'll say, oh, there's plenty of heating. If there's more than Europa's but less than Io's, then there's less heat. At all. Okay. Richard. You don't even need a differential equation. Here we just want.
Sorry, the difference.
Oh, yeah, just the difference between the two. And you're just writing it really just in terms of, you know, delta G, which is G far minus G close. If you want, I'll accept G far divided by G close. No, that's fine. Okay. Okay, so let's do class. All right. Here's what we were talking about. So we can talk about something like the specific angular momentum or the specific energy of an object when you're thinking about something small compared to something very large. And this approximation is very good in the solar system. What is an example of something very small going around something very large? Asteroids. Asteroids is a great example because we're going to talk about asteroids next. So here's the thing that we want to think about. Can we understand the distribution of asteroids, not based on the asteroids themselves, but based on the landscape they live in, the landscape with which we have no eyes to see, the landscape that is shaped by gravity? Okay? So there's this invisible force that we don't see, we can only feel and see the result of. So we're going to ask ourselves the question, as we begin to understand this work, does this describe why the asteroids are where they are? Right. So here, we talked about the total energy for mass. And you know, for the energy of a single asteroid, for example, you have its velocity, obviously, and you have the pole. Let's use this example in our mind, and I'll keep saying asteroid, but I'll change back and forth when we think about something new. So this would be the sun then, right? This would be the gravitational acceleration of the sun, and this would be the velocity. What are these two things again? Not quite.
Say radio.
Right, so we want to remember here that these two, they are scalars, so they don't have direction. Right, energy never has a direction, but energy from kinetic energy in a direction does have a form. Because these are tangential, right, you can't quite see it well, this is bold, right? So anytime you have something that's bold here, it's really v squared equals this squared plus this squared. Because those two components of velocity, right, they are separate. So for example, when I throw a ball to the left, it still falls at exactly the same rate as I drop it. Right? So here, the conversion is between this form of energy, and in this case, radial energy will be stripped down. Okay. Okay. So I can go from here to here, and this one is unchanged. Okay. Okay, we can also talk about the angular momentum, and we created this little letter called H. H doesn't have a fun term, it's just the specific angular momentum. So this is the angular momentum per unit mass. And you have some fun things in here, okay? So this is the angle, eta, that's the, typically speaking, whenever we talk about any orbit, I mean, I'll try to be consistent about this, but I'm actually super bad at it myself. So here's some orbit, okay? And this is the thing that it's orbiting around. You're going to define the angle like that. And instead of using time, which is arbitrary when you start to think about orbits, you're just thinking about how long it's taken, not how long. Where are you in the orbit, right? And that really only needs to be determined by two numbers. It's this number, eta, and this number, r. And that'll give you all of the locations in space, right? In two. Okay. So we can define all of our equations in these two terms, r and eta. How far are you from the thing you're orbiting? And, you know, if I look out in the night sky, which angle do I have to turn? Is that fair? Okay. So then we get this thing here, which is d eta dt, which is something like an angular speed, right? And not surprisingly, eta we tend to reserve for things that are angles. Any Greek letter probably has an angular component to it. Okay.
This fucking thing, why does it hate me? It's like so rude to me. Okay.
Okay. So some of you will never take classical mechanics, or one of you will never take classical mechanics. Some of you are taking classical mechanics. You finished that. Good. What's the Hamiltonian?
Never got there.
That's like last week.
Well, I'm only asking one person in this class. Okay. How's the book reading go? Okay. Open up the planetary orbit section. Really important. There's where you're really going to get your it's going to give you the background there on the mechanics. And I know one thing that happens in mechanics is a lot of algebra, it's a lot of math, and you're just sitting there going like, what? Fuck. Are you just trying to get through the algebra that you forget to ask the question, what is the thing? Okay. So Hamiltonian is different than the Galilean way of doing mechanics. So in 2500, we learned that x is equal to x naught plus VT. You remember that? You can know that still. And what comes after? X is equal to X naught plus VT. What's next? V is equal to V naught plus AT. Oh, interesting, interesting. Okay. So that means that perhaps X is not right. We have to answer that. Yeah, that would be a way of rearranging them. You're right, but that's not what we're looking for here.
Oh,
There's another term. This is currently only at constant velocity. What if I'm speeding up?
18 squared.
Yeah, something like AT squared, right? It's 1/2 AT squared. Okay. These are Gallon. I'm not spelling that right. Transformations. And I didn't. Yeah. Okay, what does that mean? That means we're talking about kinetics. How does the thing move? Right? And so what I'm talking about is I have some equations of motion that describe X and V. Right? Sometimes V in terms of A, so on and so forth. But I don't see anything about force, right? No. So what the Hamiltonian does is Hamiltonians are about energy. Okay? Hamiltonians take the sources of energy, right? And they say this is the cause of motion. Okay, so let's say this thing is conserved. If this thing changes, in order to stay conserved, the rest of them have to change. And they have to change together. Okay. That's a description of kinetics. That's a way of writing, right? R is going to be blah, 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 blah. Right? And then R, the RET is going to be blah, 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 blah. Right? And eta is going to be blah, 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 blah. And d eta is going to be blah, 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 blah. Right? That's the goal of Hamiltonian mechanics. You want to create equations of motion that care about your variables, whether that's x or y, or bx or by, based on the forces, because the forces, of course, come from they cause the motion. Remember, let's think about how these work. There's a hierarchy, right? A motion is not created with a motion doesn't create force. It's created by force, right? So if I push this, it moves. How can I push that? Good. Where did the force come from?
Great.
Energy. There are calories that I eat. There's caffeine that I drink to give me energy so that I can push things. Energy leads to forces, leads to motion. This is the Hamiltonian way. Does that make sense? And it's completely different than Galileo did. Galileo worked with what he had. The concepts of energy weren't even understood yet. Right? Okay. So let's write this out then, okay? In this case, energy and angular momentum for a particle like an asteroid, let's go ahead and conserve them. Right? That seems like a completely reasonable thing. Right? And we can make some fun definitions here. VR That's the radial component of the velocity. That's d/t. Right? We're okay with that. That's what I wrote over here. No one has a problem with that? Okay. What about this one? Am I allowed to do this?
Yes.
Yeah. It looks like witchcraft. Okay, it looks like cheating. But if I can describe one of these variables in terms of the other, it's really convenient. Okay, and let me show you why. Let's go back one step. Oh yeah, I did. Okay. All right, we defined this thing H, the angular momentum. We said that that is the product of R and V. Is this how we got there? Is it just one line? If I were to derive that for my class, who wants to learn orbital mechanics? What is L?
This is
L is angular momentum. No, don't read it. What does the L actually mean? This is a vector, right? Memorizing the sheet.
that's mass and velocity.
Mass times velocity, good. So mass, velocity, and an R. Okay, and these are vector quantities, no? Okay, now we're almost getting it. Some would say P cross R. Okay. So what is this property if I divide by M? Oh, that's perfect. Just fuck this right off, right? Good. And now we get to go one step further. How can I write L over M? Well, let's write H. Find this as H. Okay. Do I need a vector symbol here?
Yes.
Yeah, you do need a vector. It's still a vector. And the magnitude of H is what? VR. But we have to be careful. Which V? Okay, so let's look over here. We're still going to use the same example. Okay. So let's imagine I have this is the radial direction. This can be my VR, correct? And this in the direction of the angle is what? Yeah, what do we call it? V eta. Good. So how can L be defined? Or H, I should say. You like VR, you like V eta. Who wins? Right, R is out, and VR cross VR is 0. So the only component that's real, not real, the only component that's non-zero is V eta times R. Well, that's super convenient. Because that's what I got written right here. Bada bing, bada boom. Right? Okay. How can I write V eta? Is this V eta? Very tenuous, yes. It's a no. But it's not a no for why you think it's a no. Why is this not V eta? Height. This is in the radial direction, good. What is this direction? We call this the angular direction. What units are these? What?
Radian.
Radians. What units are these? Meters. What units are these?
Second.
What units are these?
Radians per second.
Ah, is this a speed? No, it's an angular speed. So I have to relate d eta dt to v. How do I do that?
Conversion.
What I said this was?
Radians per second.
Radians per unit time. What do I want? Meters per unit time. What am I missing?
Radians.
Meters. So what do I do? This, I want to relate it to this. Have the per time, good. That's wonderful.
Let's find out 2 positives.
How am I going to generate units now? Ah, okay, I see what you're doing. I like that as an idea, but that's not what we're doing. Okay, it's just R. We will use that, but differently. So let me show you why this is the way. Okay. This is some distance R. Okay. This is some angle. It's called theta. This arc length is R theta. Is that true? You know how to prove that? You know how to prove it for a physicist? What happens if you go all the way around?
Too high.
It's too high. What's the circumference of a circle? Coincidence? No, it's not a coincidence. Good. All right, so now we have almost all of the pieces. Here I have V eta, which is R d theta dt, right? So I just change it. And now I have 2 copies of R, and I have d eta dt. So my specific angular momentum H is written as R squared d eta dt. Okay? Now, right now, you don't quite understand why this is happening, why you should care. But when we get to the Hamiltonian, we want to think about things that are conserved. Okay? So if, for example, H doesn't change, then R squared has to play with the eta dt. Right? So if the eta t, if your angular speed goes up, that's the angular speed. This is the definition of angular speed. Yeah. How fast you go around an angle. Okay. Bases go down. What did we say about orbiting objects? When we get closer, do we go faster or slower? Faster. Faster, always. And now H shows us that intuitively. Okay, we're gonna get closer. Sorry, we're gonna get closer. Make this small. This has to go up. The rate of change of eta has to go up. All right. So now let's go back to that equation. Okay. And here I have on the very top, right? I wrote v squared from before. I don't know if I wrote this out. So this is the radial component, and this is the v eta component. But now we're experts, right? We're like, well, v eta squared is r squared d theta squared. I can just turn that into h. Right? So here's a component of the energy that comes from radial velocity. Here's a component of the energy that comes from going around a circle. And here is gravity. I get that, right? Okay. So let's think about this. Can I write this thing in terms of conserved quantities? I got R here. I got R here. This thing is a constant. This thing is a constant. It's only this thing that's fucking up my life, right? So if I can find a way to write this in a clever way, then maybe I'll have R just in terms of a bunch of constants. Right? Okay. Let's try. V is dRdt. Got that. Then we do witchcraft. Okay. And that's okay, witchcraft. So mathematicians, they don't want you to know this dirty secret, but you're allowed to do that in physics. Because this and this, yeah. Okay. This one, what's that? What? Is it V8? Yeah, let's write it. Excuse me? It doesn't have the R. Over R, right? Is that fair? And look at that. What's V eta? In terms of H? Yeah. So what's this? Okay. H over R squared tells us d eta over t. Well, that's awesome, right? Because now I have H over R squared right here. And I have something about R changing with something about A. Okay. So let's see if we can work this all out. So I put this thing, this is this quantity squared. I put this over here. Here are some constants that come out of the fact that it becomes squared. I have H squareds together. I have R's together. I have dr d eta. So now I have a differential equation that relates R to eta. And everything else is a constant. Does that make sense? Okay. So that's like saying the following. Right, that would be like saying d x dy equal to x stuff x squared stuff. Is that doable? Yeah. Oh. In the 1700s, figured out, right? Okay. That's a first order nonlinear differential equation. The order comes from the fact that it's just this guy. You, of course, can rearrange all of this. Not gonna be a problem. Okay, it has a unique solution. Look how beautiful that is. Okay. R at any time is just a 1 minus we want to be consistent here. I'm going to write E, that's the eccentricity, squared over 1 plus E cosine theta. Right? This thing's set by the orbit, this thing's set by the orbit, this thing's set by the orbit. Does this work? Well, what happens when the eccentricity is 0? What?
Right here.
1 over 1 or? It's just 8, right? So what does that mean? Yeah, what's that? There's a special term for that? Orbital circle. Right? You never get closer, you never get farther. And remember before we talked about we're going to throw away the idea of time. I don't care about time. I care about where I am in the location of my orbit. And now I have perfectly described every location in my orbit because this can only go, 0 to 2 pi, 0 to 2 pi, and of course multiples of that, but it just keeps resetting. Okay. So R is fully described, fully dependent on just one variable, eta. If I tell you where you are in angle in your orbit, you get the location, you get the speed, you get everything. You see how they're all dependent on this one variable? Good. And that allows us to rewrite everything we know and love. Right? Here's H. Well, I got R. Right? I can write V eta. Sure, I can show you how to manage that around if you're very curious, right? And you can write them all like this. The specific angular momentum of an object doesn't depend on the object, obviously. It depends on GM, the thing that you're orbiting. It depends on how far away you are, moderated by the eccentricity. Okay. Similarly, the energy per unit mass is just minus GM over 2m. Well, we saw. Right? And we see that when you have a bound orbit, the energy is going to be negative half the energy. Okay. I have a way of writing A. Of course, if I just flip those, that's not very unique. It's GMM over 2E. Let's say for some reason you had the energy instead of the A. And similarly, I can write the eccentricity in terms of all of these things that are constant. Okay. Here's a counterintuitive result. Enter. And let's have one orbit that is perfectly circular. E equals 0. There's a particle going around. Happy day in the sun. It looks like that egg, sorry. Okay. I have a similar particle, okay, that has the same semi-major axis, but it has eccentricity. So it gets a little closer, but it goes farther away. Now this one, let's say E equals something, some number, has the same A. Let's go. A is the same for both of them. Okay. Okay. Now, when we think about angular momentum, we're thinking about what type of process? Thinking about spinning boys, right? Specific angular momentum. In this context, which two of the two orbits has more? The elliptical one? Or you can for elliptical? Okay. Only Zori's. Okay, so why is that? Let's have a look at this one again. Here's our specific angular momentum. What is 1 minus e squared gonna do? I'm gonna make it smaller, right? For the same A in the same parent body, right, the angular momentum is reduced by the eccentricity. And the longer we sit and think about this, the more it's gonna make sense. Because I've given you two examples there, and I said, oh, those look so fun and everything else. What happens when E is 1? Zero. Is that reasonable? What's actually physically happening when I don't know, like if you imagine the orbital shape, what's the physical orbital? The most essentials that can be, right? So is there shape that's associated with what? So let's think about yeah, so like we're sitting on this like circle and it's getting wider and longer. And like, you know, this is some number. Let's do a version here. And then it goes way out our solar system. Maybe this is E equals 0.9. Right? Yeah, well, it has to get thinner, right? Because it's getting longer. Right? What a provocative question. That's exactly what we should be thinking. What is this weird solution of E equals 1? Can ellipse have an eccentricity of 1? It can, and it becomes a different shape. I won't make you prove this, but we'll do this in grad school. Okay? Ellipse. Oops, I need to color that. Ellipse goes to a parabola. E equals 1, 0, 2. Notice the shape looks the same. You can't see where it connects. Right? There's a smooth transition from eccentricity of 0.9999999 to 1. The only difference is, you see that if you look over here as well, the eccentricity, right, this thing that tells us about how squished the orbit is no longer going to be bound when it's a problem. It comes in once, goes close to the sun, and leaves. Right? So if we conserve angular momentum, and we get all the way to the bottom, and have had an angular momentum, it's going to leave again. Right? Weird. It's very weird, and it's very uncomfortable. These are the provocative questions that come when you start thinking about the Hamiltonian. Because the Hamiltonian does not permit arbitrary action. It only allows you to trade certain quantities. So we saw how we could trade radial velocity. We saw how we could trade angular velocity. Now we have this quantity called angular momentum. It's restricted. Okay. Let's do a few more things. I won't make you do this. You want to do this? You want to do this at home? You want to look these slides out? Yeah, okay. Download them. It's not that hard to do. It's just a lot of work. So, all right. Release. You can prove it. You don't care. Okay, so let's think about a body of mass m, then elliptical orbit with eccentricity E, and I want to know the speeds. Specifically, I want to know the ratio of speeds. Because now, you know, Dante asks a really important question, like, can you have E equals 1? And maybe I'm starting to really get into the idea of like space travel, right? Can I think about how to send something somewhere else? What are the possible orbits I can use? Okay. So here we have this property, you already stated it, the periapse distance that we talked about before is A times 1 minus E. That's fine. And aphelion distance, or the maximum distance, is 1 plus. Okay. So let's do some conservation of momentum. I want to build it. This is okay. Okay. All right. I need to draw this again. Body. And I'm gonna go here. This is gonna be my RP. Here, my RA. Let's assume that was good to drawing. Okay, and here's V at P. Okay, VP, not commas. Here's VA. So according to the rules of physics, the angular momentum here, H over, H is equal to L over M, is supposed to be the same as it is over here. Well, H, remember, is a cross product. So which direction does H point? You tell me. How do you do this? I don't see enough hands. Out of the, is that true over here?
There,
Ah, okay, so the direction didn't change. That was the hardest thing to fuck up. Does the magnitude change? I claimed that the angular momentum is conserved. Am I lying? Okay, so what's the trade-off? As I get closer, I go faster. So as R gets small, V gets big. So that is conserved. So I can make a statement like over here, the mass, right? Let's do H over M. I can do M. Oh fuck, I should delete it, but whatever, it's gonna be fine. MVRP like this. Right? And similarly, I can go over here and I can say MVARA. Right? But I can rewrite RA and RP. How do I write RP? What?
here, that's going to be 1 minus,
1 minus. Good. And then
and then the bottom part would be 8 times 1 plus C.
do you believe that? That reasonable? Okay, so let's use that right here. Let's use that right here. Let's set them equal to each other and we're going to drop the m's. So now I have VP A1 minus E oops, equals VA times A1 plus E. Is that fair? Well, the A's are the same, for sure. For those two. So now I have a ratio, VP equals VA. And all I have to do is a little fun ratio, 1 plus E over 1 minus E. Okay. Okay.
This has a definition, we're gonna talk about it really quickly, let's just make sure that it works according to our understanding. So if the eccentricity is real big, let's say 0.9, how does the velocity at perihelion compare to the velocity at axial?
The velocity, so the small measure.
Good, how much faster? Use for me, make a calculation, please. E 0.9. Oh, that's not what we're 9, sorry. 9. I want the quantity VP divided by VA for all of these here. E equals 0. E equals 0.1. E equals 0.9. You don't all have to do all of them, just pick and communicate. The one. Who's got 0.1? Who's got 0.5?
3.
What?
3.
3? I don't know, you tell me.
Oh, wait. Yeah, 3.
3,
Yeah.
exactly. Who's got 0.9? Okay, who's got 0.9? 199. Like that?
9, 19
You had 19 for what?
or 0.
For 0.0?
0.9.
Sorry, what did you get from here? 19?
0.9. For E equals 0.9.
Don't ever say a fraction to me. 1.2. 1.2? Is that what we said? Okay. Okay, does this make any sense? No? Okay, so let's imagine I'm going around in a circle. The velocity at the farthest point away is equal to the velocity at the closest point because there are no closest or farthest points. Velocity. Good. Now, as I increase the eccentricity by a little bit, I go slightly faster at periaps, about 20% faster than aphelion. So let me ask you a question. The Earth has an eccentricity of 0.05. How much faster are we going at perihelion versus aphelion? You don't actually have to calculate it, you can use point, right? Yeah, maybe something like that, right? Can't possibly be 20%, right? But, you know, you go up to here, here's 0.5. Have we ever seen a solar system body with eccentricities of 0.5? No. Not any of the planets, not any of the moons. That's a big one. That's a jumper, right? That's 3 times faster at perihelion than. Okay. We will talk about comets. You know, we'll talk about those things that we saw. Supposedly, they come in, they get very close to the sun, and they leave for a long time, right? But you don't get to see them for very long. Everyone's all sad. Well, I didn't get out there this weekend, right? Well, it's because they're moving quite fast when close to the sun. They're moving 19 times faster, right? And that's only if your eccentricity is 0.9. What if it's 0.99? That's 199 times faster. So now it's a race. Let's do E equals 0.999. 1,990. Interesting. So what happens as you begin to approach 1?
Go a lot more quick.
You go a lot more quick. Good, that's correct. Well, what happens?
Speaking in math terms, in application, for every extra 9 you add, you go by 9.
Right, but when you go to 1, put that into your calculator.
Explode.
Wow, it explodes, right? Because 1 divided by 0 is not fun. So here we have a ratio, okay, of the speed at perihelion and the speed at aphelion. And this object comes from very far away. So far away that we don't consider it part of the system. It passes through, obviously not at infinite speed, but that it is. Part of that assumption is that it has 0 speed when it starts. 0 times infinity is actually a finite number. Okay, so now you're beginning to understand a little bit about this coming in, going out, coming in, going out. We'll need this when we talk about comets, but less so about asteroids. All right. What's the speed of this object at a point for which its distance is the larger mass of r? So what am I asking for here? Here what I really want to know is how to describe this v in terms of how do I say it properly? Let's say I want to understand, we were talking about earlier when we wrote these differential equations that we said, well, we have these related quantities eta and r, and we know that r is dependent on eta. That's how we got so far. But now I'm very curious because I'm starting to build my own spaceship company, and I need to know how fast I'm going when I'm a certain distance from Mars. So I can use the total energy, that's on the right-hand side, and I can use these 2 pieces. These are the pieces that came with us from before. That's the kinetic energy, and that's the gravitational potential, right? And we know that they must be equal to this constant from that earlier piece. So now I can just rearrange and solve for V, and this gives me a relationship at all times, as long as you just know how far away you are from the bigger body. This is called the orbital energy invariance equation. All the rest of them have definitions too, but they're not as fun. Okay. This one you might use if you needed to calculate, say, how fast something was going in order to get a bit of boost or something. Fair? This one's not so unintuitive. There we go. Okay. Kepler. You don't have to write this stuff down, but this is stuff that you should memorize. Okay. Kepler was a scientist. He was famously given the shittiest data set from his mentor. So Tycho Brahe, famously no nose, famously died from a urinary infection. So Tycho Brahe, extremely good at using a telescope. Not a telescope. Basically a room-sized device for marking exactly where the stars are. Okay. So you wait for stars to come over your meridian. You line up this room exactly right. The room can't move, and you have it looks like a giant sextant, but it's not. You move it around, and it marks exactly the high decisions of accuracy where all the stars are in the night sky. And he made two tomes and tomes of these books. And in particular, they're watching the planets, right? So he looked at Earth, he looked at Jupiter, he looked at Saturn, all the ones that we can see by eye, watch them go across the night sky. Okay. Jupiter looks great. You know, the model of Ptolemy worked really well. Copernicus loved it. He's like, yeah, this works really great with my model. And Mars was giving them some trouble. Mercury is hard to watch. It's like during the day. So you can see it, but only sometimes. It's really hard to get perfect. Right? Okay. So Mars is giving them real trouble. And they go, here, Kepler, you fucking asshole, you keep bugging us for data. Take our shittiest data and try and go and figure this out. And that's very convenient because Mars is the most eccentric of the visible planets. And so therefore, it's the most visibly eccentric. And so he discovers three things. He discovers that the planets don't follow circles, they follow ellipses. As soon as he uses ellipses, he's like, oh shit, that perfectly describes their motion, right? And then to stunt on them even harder, he's like, I'm gonna make some laws. Okay. First law here. Equal area, equal time. Okay. What I mean by that is, here's the orbit. Let's set a clock watch. It's going to be for 40 minutes. So here's 40 minutes. And this is the 40 minutes of time. Not moving very fast. When I'm close, I'm moving faster. So that is a similar 40 minutes of time. And he said that the area in this triangle and the area in this triangle, they're the same. He was able to prove this without any knowledge of gravity, without any Hamiltonians. You have proved it in the other direction. You have shown that angular momentum is conserved, and so therefore it should speed up there. He proved it by looking at it. Ah, fuck, I think they draw out equal area and equal times. Don't ask me how you did that. He also showed that there's a relationship between the semi-major axis and the period. And you get that as well from the Hamiltonian. What is the period? Well, if I go over here, have the angular speed, just invert that, integrate over the entire course of the orbit, you're going to get period. But it's going to be in terms of the total distance. Okay. So all three of these facts were essential because Newton's theories, which came along afterwards, had to be able to describe them. Right? So I guess this is just a history lesson for us. There's a couple guys hanging out and they were looking at comets. And they were like, what the fuck are these things, bro? And they were like, I don't know. They knew for sure they were not atmospheric because people would see them in different parts of the globe. And they could use parallax like against the background stars to see that like these things were farther than the moon. So they knew that they weren't like in the air. So they were like, okay, it gets closer to us and it goes away. And they can do all these calculations to try and figure out how far these things were. They're like, what the fuck, man? I don't know what's going on. And they're like, what kind of thing like gets closer but moves faster when it gets closer and then goes away? And this guy, Edmund Halley, you may have heard of from Halley's Comet, he writes Newton. Newton, what kind, you've been talking about giving impulses. You have this F equals ma thing. Maybe we believe you, maybe we don't. But what kind of force would possibly describe that? And it's inverse square. I said, what? He said, oh yeah, inverse square will do. If the force goes at the inverse square of the distance, then all three of these things will be true. He's like, wait, excuse me? How do you already know that? Like, well, I studied it already. I showed it already. Not in this context, but in the context, in the Principia, It's geometric. The proofs of calculus are not done with calculus. They're done with geometry. Make sense? Okay. So, yeah, so that was a different world. But you can see that here. I'm not going to go through them. I guess I'll leave them up if you really care. Here's the third law. The AT integrated over one period. How to think about it alone. That's how you derive it. And then, anything on this? Yeah. So this is the cool thing. Copernicus could replace Ptolemy's model with just one description. But what's the major axis of it? We didn't even care about this, interesting, because I could fully describe the orbital motion. Just. And then that's how you get this. You want a statue? Do something really cool. Questions, comments, concerns? Okay, I will be expecting homework 3 tomorrow or today, or what's going on?